kit to treat, to modify the microstructure as well as the properties of the metal. Okay, so we can choose any parameter, any processes, and every process, every parameter of the process will influence the final outcome. Okay, so this is going to influence the microstructure as well as the properties, which is mechanical properties, because different microstructure will give different properties. Okay, so now we talk about the same TTT diagram or C curve, the same materials, the same steel, but now we want to change the microstructure into martensite. Why? Because we want to achieve the hard properties. Okay, martensite formation is a diffusionless transformation. Okay, because it is very rapid process. The diffusion of light atoms such as carbon inside the iron structure is limited. Okay, restrained because of very fast temperature changes. Okay, the atomic motion occurs by cooperative homogeneous movement of many atoms that resulting in change in crystal structure. Okay, so formation of martensite in irritated steel can be achieved through this area. Okay, so if you want to enter this border, okay, you must ensure that the original microstructure is austenite, which is gamma FCC. Right? If you obtain this austenite, then only you can obtain any final microstructure. Okay. So now you talk about martensite. Okay, forming from austenite to martensite. So if you conduct a very slow process, like a cooling process like this, meaning that you are crossing the first, this is we call it zero transformation, the beginning of any transformation from austenite, and this line is 100% transformation, and the dotted line in the middle is 50%. So once you cool it slowly from austenite, definitely you will obtain coarse or fine pellet or in between. Okay, because it's passing through this line, passing through the 100% completion of transformation. So if you want to ensure that it's entered this line, okay, the MS line, you have to cool it down rapidly without crossing this. You cannot crossing this, the first transformation line, okay, because you have to ensure that at this point, before you enter this line, before you enter this region, okay, it must be in the austenite microstructure. Okay, let's say this is the microstructure, the grain of austenite. It is solid state transformation, meaning that there is no liquid, no liquid. Okay, it is not solidification. It is already solid. It is just a different phase. Okay, from FCC into the martensite structure. So you have to ensure that before you entering this line, what line is it? The first line border for the martensite formation. So to enter this temperature, which is I guess it is about 210 or 215 degrees Celsius. Okay, to enter this temperature, you have to ensure it is still austenite. How? Because this is the indicator, meaning that you have to cool it very rapid, okay, without delay. Let's say at 500 degrees Celsius, you reach 500 degrees Celsius after 1 second. So meaning that you are already crossed. Maybe it is there is a tendency that you are crossing this line, the 0% line. Okay, so to do that, you just refer to this diagram. This diagram already provided from the supplier, so you need to know how to use it. Okay, so yesterday we talked about how they create this diagram, but today we learn how you can utilize this diagram. Okay, each diagram different depending on the types of steel. Okay, for this example, it is EU-tapered steel. Okay, you cannot use this diagram if you still containing 0.2%, carbon? No, definitely not, because you won't obtain the same microstructure as well, similar to the eutectic steel. Okay, every TTT diagram is unique for very specialized for specific type of steel. Okay, so then by cool it down rapidly. Okay, cool it down rapidly, you can see that it's entering this region and complete at this line, meaning it is 100% martensite. Okay, so look at the time. It is second, meaning that you have to do it quickly, reaching the temperature 200 within a second. Okay, and completely 100%. Okay, martensite when reaching 100 degrees Celsius or below. Okay, slightly below. So after that start transformation at this point, okay, and then at this point, it is roughly 50% austenite transformed into martensite, and these are the 100%. Some of the diagram you may see is written as 50% here, but here is right. It is written as 90%. Okay, it is just a different composition or maybe different textbook. Okay. The formation of martensite in eutectic steel, okay, there's a inside the retained austenite. We call it retained austenite. It is not really austenite. Yeah, retained austenite, where the carbon is a trap in the FCC structure, forming a BCT structure. It will looks like a needle-like structure like this. Okay, this is martensite plates. It is very tiny. The ratio the length ratio to the not volume, uh, the, over the diameter. Okay, the aspect ratio between the length and the diameter is really high, so that it will give a low strength for the impact load at transverse direction. Okay, uh, right. This is the martensite, different martensite at different temperature. If you quench to room temperature, and if you quench at very low temperature, it will give a different martensite formation, meaning that the temperature of the quench medium will influence the martensite formation. In this case, for the eutectic steel, if you greatly reduce the temperature changes, or why this matter? Because this will influence the cooling rate. Okay, this for example, austenite temperature is 750. So to achieve this, it is about delta T is about 7 to 5 only. But imagine this one, um, the delta T equal to 850 degrees Celsius. So over per second, this one is higher cooling rates and very rapid cooling, and it will produce greater martensite formation. Okay, so we can control the process. Okay, parameter such as the quench media, cooling rate, of course, and then the duration, the temperature, and everything. It will greatly improve the microstructure, and if the microstructure is changed, is different, so you will obtain different properties. Okay, so of eutectic isothermal diagram, it is a diagram that the same C curve or TTT diagram or isothermal diagram, but different carbon composition. And if you look at this diagram, you may see a different, okay, which is there are a pro-eutectic microstructure. Okay, pro-eutectic microstructure. Right. So, of course, if we quench at a higher temperature, we will achieve, remember the, sorry. Right, the phase diagram of the steel, okay, this is phase diagram of the steel. Okay, this is alpha plus cementite. Okay, this is austenite. Okay, let's say you have 0.4%. Okay, for uric it is about 0.8% carbon. Okay, let's say we talk about 0.4, right? From austenite temperature is here. Okay, this is austenite temperature. And then you quench to the temperature, let's say this is 750. Okay, this uric temperature is 7 to 7 or 7 to 3 degrees Celsius. So let's say you quench from this temperature, what is it? Maybe 800 degrees Celsius. You quench to 750. So meaning that you have transformed from austenite into this phase, which is the mixture between austenite and alpha, ferrite alpha, ferrite. This is ferrite alpha. This is austenite. So meaning that if you quench to this 750 degrees Celsius, you will obtain a transformation from austenite into ferrite alpha. Okay, unlike uric steel, which is 0.8%, okay, you quench to the temperature below that, this temperature, you will obtain pearlite, which is a lamellar structure of alpha slash cementite. Okay, so now we talk about off uric, meaning that you are going to have a pro-uric microstructure, such as hypo-uric or hyper-uric. So in this case, you will have a different microstructure if you quench at if you have different uh, composition. So if you want to tailor the properties, you must know what is the properties for each phases. Okay, so if you obtain if you want to obtain how to say this, maybe it's not practical, but it can be done. Theoretically it can be done. Okay, let's say you want to have this microstructure, which is alpha. This alpha. Look at this. All right. So let's say you have this temperature from 800. You quench to this lah. Let's say from okay. All right. Okay, I'm sorry. Okay, let's say you choose quench to this temperature, and then you hold at this temperature around 700 or 650 until benda ni mn apa ni? About 50 second. 50 second, okay? This time. 50 second, you hold until this, and then you quench to room temperature. Okay, can you guess what is the phases of your final microstructure? Final microstructure. What is it? Can you guess what is the final microstructure?
Gamma plus alpha.
Gamma plus
Alpha.
alpha. All right, gamma plus alpha. Okay, so let's think. If we refer back to the phase diagram, okay, This is gamma. This is alpha plus gamma. This is alpha plus cementite. And this is gamma plus cementite. Okay. Right. What temperature is this? 7 to 7 degrees Celsius. So now you quench to the room temperature. How can you obtain gamma? So maybe you may ask, what gamma do here? Isn't it? Okay. So gamma is yes, but we don't call really gamma. We call it retained austenite. Okay, retained austenite. But the mass microstructure form if you change austenite to the room temperature. You let austenite reduce rapidly to the room temperature. Okay, what happen is gamma will transform into martensite. Okay, and the formation of martensite, it is not the whole structure of your microstructure is martensite. Okay, martensite, remember previously I've shown this microstructure. Okay, this one. Okay, you can say, oh, my microstructure having martensite, but actually inside the martensite there are, at the background here, it's surrounded by gamma. Okay, but austenite, we call this austenite as a retained austenite. Okay, austenite. But when we discuss about the final microstructure, basically we don't say that, oh, I got retained austenite. No, basically we highlight the formation of martensite, because whatever is this, there's no 100% martensite. There must be a portion of retained austenite here. So we still call this is our final microstructure containing containing martensite. So when we talk about this process, okay, when you let it cool rapidly after 50 seconds of soaking at this temperature, which is 690 degrees Celsius, okay, you let it holding at this temperature for 50 seconds, and then you quench. So meaning that there are some portion of austenite, only maybe 20% or 30% is ferrite. Okay, what happened to the rest? 80%. 80% rapidly quenched to room temperature, meaning that the austenite, the 80% austenite here will transform into 80% of martensite. So you want you can modify, you can customize this. Okay, you know the ferrite is soft and martensite is hard. Okay, if you obtain 20% of softness and you measure the hardness, you measure the tensile strength, you measure all the properties, you think that, oh, there's some there are room for improvement. I want to increase the strength a bit. So for that, you can increase this, okay, to 30% maybe. So how much it will influence? And then you as an engineer, basically you are required to provide this data. Okay, you test it several times and provide the database, and later on when the supervisor to give the instruction to the labor, whatever the low level worker, they just apply it. Okay, whatever the numbers that you have recorded. Okay, so this is the task that the responsibility of the engineer when they works with the process. Okay, so the application. Okay, tempering. This is a process that basically traditionally people do when they want to make tools, okay, cutting tools or whatsoever, right? Like a knife, a hammer, okay, a hammer or whatever is this. It's a benda yang tajam kan. The tools that for cutting. Uh, yeah, if you want to cut something, the tools must be very hard, okay, because it need to maintain the sharpness of the cutting area. Okay, so the knife, for example, okay, the blade must be very sharp enough. Okay, to obtain the to maintain the sharpness, uh, the hardness properties is required, because it don't change plastically upon impact load. Okay, maksudnya dia tak mudah tumpul lah bila kita bagi impact load. dia tak merubah bentuk sharpness dia. Okay, let's say this is the knife. Okay, the sharpness at this blade. Alright, so it must maintain a certain degree of hardness. Okay, so that it won't easily deform plastically. Okay, so tempering, we quench. Okay, during the tempering, what happened is, okay, so now we have this C-curve diagram or isothermal diagram. So when we talk about quenching process, okay, it is very rapid. What happened is there are a different degree of cooling rate. Okay, for example, if you have this kind of cylindrical shape of component, any engineering component, you conduct the quenching process. Okay, what happened is outside, only at the outside will experience very rapid cooling. Meanwhile, at the inside, it is slightly slower cooling. Okay, so we can translate into this diagram. This is outside. Okay, this is inside. So inside is slightly delayed. Okay, it reached the temperature of MS, or the starting of Martensap formation, slightly later than the outside, because outside is the first point reach room temperature. Okay, so outside region is the first point that reach the temperature 200 degrees Celsius, which is the MS temperature. Okay, meanwhile the inside, of course, the diffusion of the heat is travel through the mass. Okay, so inside is still hot and it takes some time to release the heat from the inside. Okay, so it is a bit slower. Okay, you need to control to ensure that inside will experience Martensap formation completely. All right, so to do that, you have to ensure that inside also does not crossing this 0% or the beginning transformation formation. Okay, that's issue number one. Issue number two, there are different cooling rate. Okay, so different cooling rates, what happen is it is easily cause, okay, the different rate between outside and inside will easily cause cracking. Okay, so this is what normal quenching and tempering process. Okay, after we cool it down, and then this is complete of quenching process. Process number one is quenching, and then we reheat for the tempering process. Okay, tempering process, this is tempering process. We reheat and holding at some time, and then slowly cool. Okay, or even rapidly cool is does not affect so much. Okay, so that this one is conventional. Okay, conventional quenching plus tempering process. So there's another improved process. We call it mild tempering process. Okay, mild tempering process. How? Okay, mild tempering is actually a modified steel quenching procedure to minimize distortion and cracking that may develop during uneven cooling of the heat treated materials. Okay, this is uneven at the outside and at the inside. Okay, during the first quenching process. So mild tempering, what is the purpose? The purpose to solve the problem, the uneven cooling rate between the surface and the inside materials. Okay, upon cooling, upon quenching process. Okay, so how do people do this? Okay, right, this is the quenching at the temperature just before the martensite formation. We don't want martensite form at uneven transformation time. Okay, so now we know that there is a curve like this. So we can utilize this unique shape of the 0% transformation line. Okay, how? Okay, we quench just before this temperature. Okay, let's say we take 250 or 230 degrees Celsius. 250 degrees Celsius. For example, like this example, okay, we hold this temperature, okay. 200 degrees Celsius, 250 degrees Celsius consider still high, not this one. Okay, 250 degrees Celsius still high, and the microstructure still austenite. Okay, we hold it for some time, and then just before we entering this region, we quench it to the room temperature. So by modifying this process, we still allowing the transformation from austenite to martensite. We still get martensite, okay, similar to the conventional quenching and tempering process. Okay, so we got martensite. The martensite is still the same. You still need to have um, tempering process, okay, to temper the weak or brittle martensite. Okay, you do the tempering process as normal, and then you get better tempered martensite. Okay, we call it mart tempering. What is the difference? The difference is only this. Okay, uh, just a small modification, but with the knowledge, the engineer come up with the solution. Just having this holding time before the beginning of martensite formation. Okay, do you understand?
Yes.
All right, very good. Okay, uh, there's another type of tempering process. We call it house tempering. Okay, earlier we talked about quenching, conventional quenching plus tempering, and then number two, mild tempering. Okay, which is just slightly modified the process of conventional quenching and tempering, and then next is house tempering. Okay, house tempering is an isothermal heat treatment that produces a binite structure. Actually, it's not martensite, it is binite. This heat treatment process provides steel with better toughness and ductility. Okay, so it is just a normal heat treatment process, which is you quench at certain temperature to for what? Just to obtain the lower binite. Just want to obtain lower binite, but the temperature just slightly above the beginning of martensite formation. Okay, not 300, not 350. Okay, 350 you still obtain lower binite, but this one it is slightly lower. Okay, the final microstructure is lower binite. Okay, the effect is similar to the tempering. Okay, as tempering is an isothermal treatment that produces a binite structure. This is a treatment process provides steel with better toughness and ductility. The keyword is toughness. Okay, toughness and ductility. Okay. Another important point for house tempering is basically um, I I think all small components such as the screw bolts, they use this heat treatment process. Why? Why screw, nuts, bolts using this process? Okay, basically the point is small component. Small component basically they utilize this house tempering process. So why screw nuts and bolts require this kind of process?
Wear resistant.
Okay, wear resistant. What makes you say that?
Sebab dia nak pakai lama nuts dengan bolt tu.
Okay, yeah, nuts and bolts ni memang kena pakai lama sebab dia joining. It is a joining between two component. If it is easily corroded, easily wear off, easily broken, so the structure needs means the structure will collapse. Okay, so and another things at the joining is the most yeah is a region where experience stress concentration, isn't it? So some static load or dynamic load or accidental load uh, will focus at joining. okay, where there is a screw, nuts, and bolt. Okay, so the toughness, okay, other than wear resistant, toughness is the most important. Okay, because it's that's the most critical part. Okay, if you have, for example, joining at the bridges, okay, at the bridge there's some metal, there are several metal parts. It's being joined by the screw, bolts, and whatever the fastening method. Okay, so imagine there's a accident on the bridge. Okay, there's some impact load happen on the structure, so the screw, nuts, and bolts is really critical at that point. So if they are brittle, they are soft, meaning that they cannot support the structure. So that's the reason this small component using house tempering. Another thing, it is because they are small. Okay, if the bolt, screw, and nut is large, maybe house tempering is not practical. Why? Because of the structure is small, whatever the effects that experience from the temperature, outside temperature, to the 300 or 200 something temperature, they experience, okay, like a um, real quenching process, okay, like a mountaintop formation, because of very large temperature difference, okay, and the small component has a small volume, okay. So and then it will utilize this kind of house tempering process. Okay, so in summary, isothermal transformation diagram make possible the prediction of microstructure. See, you just need to know there is a diagram, okay, which called isothermal transformation diagram, where we can modify the microstructure of your product, okay, by just following whatever heat treatment method that suitable for your component. Okay, metal synthetic steel are the hardest and stronger, yet most brittle. Okay, so it is always associated between um, hard and brittle. Okay, imagine when we talk about hard, imagine like a brick, glass can. It is very hard, but they are very brittle. Tempered martensite is very strong, but relatively ductile to the martensite. Okay, and binite has desirable strength ductile. Binite is in between the martensite or tempered martensite and the ferrite or pearlite. Okay, so that's the reason uh, it is not as strong as tempered martensite. Okay, fine pearlite is harder and stronger and more brittle than coarse pearlite. Okay, yesterday we talked about the coarse and fine pearlite. Okay, they are all pearlite. Remember, pearlite having the lamella structure like this one, and the fine pearlite having a fine microstructure like this, but still inside the microstructure, the faces is pearlite. Okay, semua pearlite lah. Okay, so fine microstructure is stronger, finer, stronger. Okay, because of the grain boundary. Okay, always remember this. Okay, at this point, you can utilize the benefit of grain size. Okay, without changing the types of alloy. Meaning that, let's say in your company, your boss asks you to improve the strength. They don't want to spend money on changing the material. If you change the material, raw material, meaning that you need to change the supplier, you need to do the investigation to verify whether the supplier is correct or not. Many things to need to be considered. But now the objective just to improve the mechanical properties, just to improve the strength. So meaning that you can tailor the grain size. Oh, sorry, the grain size. Just conduct the heat treatment process and change the grain size. Or if you want to improve the ductility, again, you can increase the grain size. Okay, so that it will be more ductile, more softer, less hardness. Okay, something like that. Okay, one benefit of mud tempering is that it reduces the cracking. Okay, why? Because inside and outside components during the quenching will experience different cooling rate. Okay, that may cause the thermal stresses. Okay, and of course residual stresses due to the varying geometry. Arc stamping is a hardening process for metal which yields desirable mechanical properties such as high toughness and ductility. Okay. All right. I think that's all for this slide. Before we continue, another slide. Okay. Let's take a break for 10 minutes and come back later at 3 o'clock. 15 minutes lah. 3 jam. 3 jam. Pukul 3. Alright, can we continue at 3 o'clock?
Can, Doktor.
Okay. Alright,
Yes,
stay je kat situ. Kalau you nak minum-minum pun boleh. Tapi jangan lari Okay. Alright, see you again in 15 minutes. Okay, kalau ada apa-apa nak tanya, boleh tanya. Saya ada kat sini.
Yes, Doktor.
Right. I'm going to give a brief on the assignment. Okay. CMM 2613 and material science, the group assignment. Right. This is the instruction. Actually, you are going to again train yourself on how to get a correct information, because I'm quite surprised because according to the last assignment given to you, which is short assignment 3 as well as the test 1, it is I think it is a good training for you to really understand how to judge the information that you receive. Okay. The thing is, for example, in the test question, okay, the question asks you to find the metal that having interstitial structure or diffusion, and another alloy. Another one is substitutional. Okay, but still I found most of the interstitial, especially, it is most of them are not really an alloy or metal materials. Okay. Because if I try to Google those information, I can easily obtain the information. Now I realize that you need to practice until you get a very useful experience. Okay, in learning. I think this is the skill for lifelong learning. Okay, so you faham ke tak? So never mind. You need to do more so that you experience in this practice. Okay. So for the group assignment, it is slightly different from the short assignment and the test, because it's train you to work in a group. Okay. So the objective of this group assignment is to increase student ability to understand materials and the science behind it. And then number 2, to train the student for lifelong learning by searching relevant information related to materials from various sources. So when we talk about sources, last time
Doktor tengah share ke, Doktor?
Sorry.
Sebab kami tak nampak slide.
Yes, tak nampak. Memang saya terlupa. Okay. Okay. So sekarang saya share. Okay. So this is the assignment. Okay, ni ke depan je lah. Ni objective. Alright. So number 2, to train the student for lifelong learning by searching relevant information related to materials from various sources. Okay. So when we refer to any engineering knowledge or science knowledge, we need to know what is the actual sources. Okay. So for example, if you read the news or read any information, sometimes for example, like rumors, something like that, or any what we call it, any whatever news from the please. Okay. So sometimes you might think that, oh, because of the publisher, you think it is not maybe the sources is not really strong enough to support the reliability of the information. So same goes to the academic or research perspective. Okay, when we find the information, for example, about the alloy, the compound. Okay, if you search randomly from the internet, and if the publisher is a very good society of any science area, for example, in materials, there's a various material society. Okay, that sources may be a very high reliability. Okay, if it is coming from any what we call it any profit making agency, for example, if they sell aluminium, they may highlight only a good side of the aluminium, for example, only the good side of their product. Okay, that one is uh, less reliability in terms of the information. Okay, so you need to get experience. Okay, get experience, and then from that it will fasten up your process to making a report or answering or do any solving any engineering problem. So point number 2 is really critical for this group assignment. Okay, number 3, to train the student to present their work related to the characterization and method of improving the materials. Okay, there's a new elements here about how we can improve the materials property. Okay, in the previous chapter, we talked about strengthening mechanism, we talked about heat treatment process. Those are the processes to improve the mechanical properties. Why? Because I want you to know that the microstructure, whatever the microstructure that we obtain through the process of the improvement, it will really affect the mechanical properties. That's very important point. As a mechanical engineer, you should be able to have this kind of knowledge. Okay, so the deadline I put here, 2nd of July. It depends on the situation. Before that, may I know anybody are still in the campus right now? Anyone? No? Okay, I assume there's none of my students are in the campus right now. So if you are in the campus, I think you can finish up this quite fast, because you can easily access the library, what we call it, online access without using the third party VPN access. Okay. So for this, what you have to do is you need to prepare a PowerPoint slide uh, to um, just like a presentation. Okay, but your presentation will be recorded in the video. So you need to submit 2 files. One is the PowerPoint slide, and number 2 is the video itself. All right, and then you have to submit through the e-learning. Okay, under the folder name group assignment. I haven't yet created this one. Okay, but I will do it. The deadline is 2nd of July. So what need to be in the report is the introduction of the material. Okay, I will give you the names of materials that you need to study. Okay, in introduction, basically we introduce about the material. For example, if it is copper zinc, which is a brass, you introduce what is the brass, what is the elements constitute, what is the mechanical properties, chemical properties, and many other characteristics. And then point number 2 is the content on the phase diagram of that particular alloy. For example, in the plumbum tandem alloy, okay, you need to explain how the phase changes, okay, how the phase change, and how we can determine a specific phases. All these criteria need to be present in your report. Okay, this is example. For example, you have plumbum tandem. What is plumbum tandem? Plumbum tandem is basically a soldering material that we use in almost all electronic packaging. Okay, if you want connect to one terminal to another terminal, one component to another component, we are going to use tandem-based materials. And plumbum, maybe nowadays they try to reduce the use of plumbum, but the well-established, the most popular long time ago is plumbum sternum. So the application is very wide. The various composition of plumbum sternum is widely used in the industry. So it is this is the types of phase diagram for plumbum sternum. Okay, there are different category of the alloy. One is a hypoeutectic alloy. Where is hypoeutectic alloy? It is here. Okay, hypoeutectic, and this is eutectic alloy. Okay, within these regions, meaning that below this horizontal line, between this to this, it is hypoeutectic, and between this region to this region, it is hypoeutectic. So there are several types of phase transformation. You can discuss on this. You can discuss on this. You can discuss on the this one also. You can discuss at the eutectic. You can discuss at the hyper. You can discuss at the region where involve the transformation into single phase of beta phase. Okay. All right. So this is the content need to be there when you discuss about the phase diagram. Okay. And then the third point need to be present in your report is the method to improve the material properties. Okay. You can list down the method must be relevant, not just a random improvement. No, I don't want that. Okay. Must be relevant to your alloy. For example, like this plumbum sternum. Okay, there's so many problems. You highlight the problem. Okay, for example, we want to eliminate plumbum. You can replace with copper. Okay, you can search information, not just guessing process. It must be established, reported process. Okay, from the reliable sources. Okay, trusted sources. You're not just guessing, oh, it can be combined with copper to replace plumbum. No, no, not like that. Okay. Other than that, maybe improve in terms of the hardness. Okay, by instead of only sternum plus plumbum, maybe we can add more, such as silver. Why we add silver? Highlight it. Maybe to improve the mechanical property. Maybe to improve the material stability upon the aging process. There's so many. You need to search from the reliable source. Okay, you cannot do it last minute because you won't be able to find it because you never train your search engine. Okay, if you do it last minute, your search engine such as Google or whatsoever, they don't well train enough. Okay, because why? Because they never search for this kind of information. They don't know which one is you spend more time on that particular content, so that they are not smart enough. Okay, so meaning that you cannot do it last minute. You can start from now, and then one day maybe 20 minutes or 30 minutes spent for searching information. Later, after 1 month, after 4 weeks, 3 weeks, maybe your computer is will become smart enough. Okay, and then you conclude based on the information relates from point 1 until point 3. What is the conclusion? And then references. This is very important. I want to know what kind of reference that you refer to, and then the attachment if it is relevant. Okay, if it is not relevant, you can just omit this one. Okay, the rubrics. Okay, special peer review evaluation. Peer evaluation. Okay, I will provide a Google form. Each of you need to evaluate your friends, your group member. I will assign a group member for you. You need work for it. You cannot choose your friends, okay, because this is the real world happen nowadays. It is randomly, like during the pandemic now. You never see your friend's face, okay, but you need to work with them. So please, okay, and then only 45% on the content, okay, but the rest in your attitude. Okay, this is your attitude. Okay, this is also the other skill, which is reporting and then presenting. Okay, these are communication skill, right? These are the integrity or ethic. Okay, jangan main-main hantar lambat memang kena tenyih lah dengan bos Okay, content 45%. Cukup tak ni? 20, 40, 55. Yes, okay. So this is the rubrics. I'm going to evaluate based on this one, and this is a contribution marks from you. Okay, those this is 100%, but for your total mark is only 10%. Okay. Okay lah. Sebulan punya kerja kan. Alright. The project title. There are 11 titles. Okay. This kind of alloy is assigned for each group. This is group 1 until group 11. And then, oh, okay. Mana this? Alright. The list name. The list name. I'm going to show with you the list name. Sorry kejap Okay. I'm going to upload this in the e-learning. Don't worry. Okay. So these are the group names. Okay. Your group member. Group number 1. Okay. Group number 1. You need to identify your friends. Okay. Aaron, Ikhtiaruddin, Alvin, Hongchu. Okay. Semua ada Alright. So group number 2. Hakim, Pridoy, Jacob, Johnny. Group number 3. Showway, Kahmun, Jinyang, Hazibut. Okay. Group number 4. Mahbubur Rahman, Nusrat Alam, Muhammad Zuhair Akmal, Zulfadli. Group number 5. Muhammad Amar Syahmi, Muhammad Faiz, Muhammad Nizam and Muhammad Zuhaimi. Group number 6. Ong Sing Chi, Pradhanartha, Rangga Ramadhani Taruna, Tai Yo Wen. Okay, group number 7, Abdul Rahman, Ahmad Kamil, Amirul Hazim, Induk Zaris Syuhada. Induk ada di sini?
Ada, Doktor.
Okay, good. So itu kawan-kawan awak lain program tapi okay. Baguslah you mix dengan program lain. Alright, group number 8, Karim Essam, Mustafa Muhammad, Muhammad Amirul Iman dan Muhammad bin Hazman. Group number 9, Muhammad Faik Idlan, Muhammad Fikri, Muhammad Firdaus dan Muhammad Ifat. Group number 10, Muhammad Rezwan, Nur Iqbal Putra, Nur Fatinatul Aisyah, Nur Adriana, Ardini. Okay, dan selebihnya group 11, Umar Qayyum, Muhammad Akid, Yusuf Amir Mustafa, Anas Farhan dan Muhammad Zahir Fitri. Okay, semua ni ada ke? Alright, I'm going to upload this in the e-learning. I'm going to share it with you in the WhatsApp group also. So, okay, the title is actually the alloy name. Okay, okay. This is I just randomly select based on my experience of working with these materials. Okay, but if you think there's so much burden for you, you are unable to understand what is the application, so difficult, and you want to change to another application, for example, you want to change it into magnesium titanium, for example, because you think the application is so what we call it, it's so canggih lah, okay. So amazing, very brand new application, very smart for the robotic, for the sensor, for example. You think that one is most interesting to be studied, you can propose in the WhatsApp group, okay, so that the rest of the student in the class know that, and if they have the same intention, they can avoid that kind of particular alloy. Okay, this is just the name of alloy that I think there are some application of it. And if you think you have better idea, you can propose and you must discuss among your group member. Okay, so I think that's all for the assignments. Any question?
Doktor, presentation dalam bentuk slide kan?
Dalam bentuk video. Slide dan video. Maksudnya slide tu
Kita
nak buat video.
kita present lah slide tu maksudnya.
Ya betul.
Ada minimum berapa page ke berapa?
Tak ada minimum.
Tak ada minimum. Okay.
Sebab the method, I think the best method if you unable to upload because the movie file is too large, you can just share the link of the YouTube. Let's say you upload to the YouTube and make sure or you can share in the Google Drive the link to me, and I need to keep the video in the Google Drive so that it will be stored permanently. Okay, so I assume that my Google Drive account is will be permanent until I die or until I retire, so that I need to have that video. If you upload to the YouTube, you just share the link and I will download it and store it in my drive. So don't worry about the size of the video. Okay, tapi jangan sampai 100 giga kan, macam kagum benar saya tengok. Okay, alright. So the presentation style is like that. Okay, you can act properly during presentation. You don't have to worry about spontaneous, but I think it shouldn't be a problem. All right, but make sure your voice do not using Siri or whatever the narrator application. Okay, jangan guna suara robot. Okay, use your own voice. This is the chance to show how nice your voice is. Okay. Ada lain tak soalan? Is there any other question? Tak ada Kalau tak ada kita sambung kita punya kuliah. Kuliah kita ada lagi 20 minutes. About 20 minutes. Okay. Continuous cooling transformation diagram. Okay, it is about, it is not much different with the TTT diagram. Okay. So, in this case, the outcome from this topic is to understand the hardenability of the steel. And what is hardenability? I think you have some experience in the lab, right? Where one of the lab module is Jomini and quench test, which is the test on the hardenability. Okay, so I think it is the theory is now, okay, which is the hardenability. So by the end of this lesson, you should be able to understand how and why Jomini and quench test is performed. Okay, able to use CCT diagram to predict phase transformation during continuous cooling heat treatment. Okay, what is this? See, from austenite phase, merah to austenite. Quenching, okay.
Doctor, we can hear you.
This is the quenching process. How they run the quenching process. Alamak. Boleh nampak ke video ni?
Nampak.
Okay. So tadi saya takut sebab saya share video ni dia jadi macam ni. Dia terus tak boleh display. Okay. Ni satu lagi. Macam tu lah rupa dia. Dia buat heat treatment. This is the heat treatment process. Okay. Versus time. Versus distance. The temperature reduction at one time. Okay, for example, after quenching, you quench in the water. Okay, this area already reached room temperature, but at the center, this region exactly at this point, I mean that from this body exactly at the center, is still high temperature. Temperature maybe 200, 300, something like that. Okay, it's very very high temperature. But this one is already.
Doktor, slide hilang.
Slide hilang pula. Okay, slide hilang. Suara boleh dengar
Boleh.
Okay, sekarang nampak tak slide? Tak nampak
Nampak.
Okay, nampak Alright. So what I'm trying to say is, if we do quenching, the surface, this is surface, we'll coat it first, and then this is center, the core region. Okay, it's still at high temperature the moment you immerse in the water. Okay, so in continuous cooling heat treatment still is undergoing a continuous cooling as opposed to an abrupt rapid quench. Okay, so the transformation from arsenide to pearlite occur over a range of temperature rather than a single isothermal temperature. So CCT diagram is used to represent which type of phase changes will occur in the material as it cools at the different rates. So CCT ni meaning that it is just like a isothermal TTT diagram, but for the CCT, okay, you don't quench at specific temperature. Okay, you just quench at normal temperature, and then you will obtain similar phases like for example, like this. Okay, CCT diagram, TTT diagram is like this. Okay, like this, you can obtain phase like pearlite, bainite, and martensite. But CCT diagram is only a continuous cooling process where it's covered this region only. Okay, this region only. So meaning that if you cool it without quenching, you cool it normal cooling rate in the air or in the furnace, you can get both polite, coarse polite and fine polite. Okay, so imagine this is TTT diagram. Okay, so why you need to quench to this temperature and hold at this temperature just to obtain fine polite or coarse polite, whereas you can obtain it by continuous cooling process. Okay, continuous cooling process. This is the beginning. Without quenching at this high temperature, for example, 650 degrees Celsius. Okay, no, you don't need to. Just continuous cooling, you can obtain fine polite or coarse polite. Okay, and then the next thing is hardenability. Okay, the hardenability of metal alloy is the depth of to which a material is hardened after putting it through a heat treatment process. Okay, uh, it is not a hardness. It is the ability of material to be hardened. Okay, do not confuse with hardness. Okay, basically, if you want to investigate this property, which is the hardenability properties, not hardness. Okay, we want to identify the hardenability. Okay, we will conduct Germany and quench test. Okay, the Germany and quench test, if you conduct in the lab, material science lab, you have learned this. Okay, you have this from the austenite, you rapidly quench starting from this point. And then you grind the surface so that it will become flat surface. And then you conduct the hardness test. Okay, to investigate these properties, hardness testing is required. Okay, hardness properties is an indicator or the measuring tools to determine the hardenability. So if you conduct the hardness test, if you remember for the chapter 5, mechanical properties, there's a topic on hardness testing. Okay, Victor's hardness or Rockwell hardness or whatever testing. Okay, for example, if the Vickers hardness using the diamond indenter, you indent on this flat surface and you may see the various size of indenter. Okay, the larger the surface being indented, so this is the size that you measure. The larger the D size, okay, the softer material, more data. This is hard because very small, tiny indentation that can be done. Okay, very tiny surface being indented. Okay, of course there is a plastic deformation occur. That's the reason you can see the shape of indented, lekukan. Okay, bila dia melekuk dalam tu, size lekukan tu menjadi indikator untuk how soft or how hard the surface. So if you see this kind of variant size, so meaning that this one is hard, this one is soft. Okay, this one will cool first, cool rapid. This one will be cool slowly. Okay, slowly. So that's the reason it will become large indenter size. This is small indenter size because it is hard. Okay, so so the Gemini test involved here. Okay, blah blah blah. You can read it. Of course, you need to heat it up to austenite and then quench at the room temperature only at the end of the materials. Okay, you insert the steel and then you open up the water. Nampak tak video ni?
Nampak?
Okay, good. So nampak. Okay, sorry Bila dia play video tu, dia jadi macam tu. Okay. Alright. Nampak tak slide ni?
Nampak?
Nampak?
Okay, good. Okay. So cooling rate at the end of the quench test will be cooled very fast, and this is the flattened surface on the specimen. The water will be injected at this end, so this will be it will cool at if we model the time here. This is number one, and this is the last one. Okay, this is the first. Okay, first point where reaching a room temperature. Okay, so we take several points from this to this distance. Okay, after the farther away from the quench end, the higher the. Okay, so the meaning of this sentence, if the high hardness, let's say this is hardness, let's put this as a 200 hardness viscous, the value at this point, okay? And if this value can be maintained up until the distance farther from this end, let's say maybe it is around 196 viscous hardness. So meaning that the higher the hardenability. If the result shows that here is 200 and here is 50, okay, so meaning that this one is low hardenability. Okay, so this one is high hardenability.
Doktor kami tak boleh nampak slide.
Oh, tak boleh nampak ke? Okay, sekali lagi saya share. Okay, nampak tak ni slide saya? Slide. Nampak tak? Okay. Right, kita balik dah Okay, so from this point to this point, if you can maintain the hardness, this is what meant by this sentence. Okay, for example, the hardness, you test this point is the indentation test. So many points. Okay, you can maintain the value. For example, this is 200 viscous hardness, and this is about let's say 190 hardness viscous value. So meaning that it is almost about the same. Meaning that this material is having high hardenability. Okay, but if the value here is 200 and here is 50 hardness viscous value, so meaning that for this alloy it is low hardenability. Because why? Hardness value, hard properties is coming from the martensite. Okay, from the martensite. So you can assume at this point it's having lots of martensite. For this material, even though it's cooled at the same time, okay, maybe at the same time, okay, need temperature time equal to 0 second, time equal to 50 second. This one also 0 second, this one also 50 second. But this alloy, jangan confuse pula. Alloy 1, alloy 2. So alloy 2, okay, even though this point is experiencing 50 seconds of cooling process, but it is able to form martensite. So that's the reason it have very high hardness, even though the distance is farther from the end quench. Okay, so this material is considered as high hardenability. It can be hardened even though the cooling rate is slow, right? Why? Okay, number one, because of the alloy content. Number two is because of the size of the material and many others effect. So high hardenability means that it is able to form a complete high hardness, even though the distance from the time to cool it down to room temperature is long from the point, this point, and quench point. Okay, so if the distance at the far from the quench end is lower, so means that this is low hardenability. Okay, the martensite form at the end, and this one is ferrite formation. Okay, the continuous cooling rate is forming from the quench end test. Okay, so we conduct this distance from quench hardness. What's the difference between these two? All right. Every point from the distance 0 and the distance far until 80 mm will experience different cooling rate. Okay, the cooling curve, we call it cooling curve, will different at every point. Okay, at the distance 0, which is A, it will experience quenching process. Okay, quenching process. All right. So for the quenching process, of course, you will obtain 100% martensite. Okay. And then for the point B, somewhere here. Okay. Somewhere here. So point B, there are slightly less martensite formation. Why? Because it's already go to this point. Okay. When it's crossing this line, what happened is there is the beginning of phase transformation. Okay, there's some percentage. Okay, the formation into pearlite. Okay, the beginning of pearlite formation. So what happened is it's contained, okay, some amount of pearlite. They call it modular pearlite. And what about the rest? The rest will experience quenching, forming martensite. Okay, and then at the distance farther from the quench end, okay, will become more slow cooling rate. Okay, so it will completely transform into fine pearlite. Okay, fine pearlite, 100%. There's no martensite. Why no martensite? Because it is crossing this line. What line is it? It is 100% transformation. Okay, this is the begins, this is the end, meaning that it is 100% transformation. Okay, so you end here. So this region is fine pearlite. Okay, what about D? For D, it's begin here, it's ended here. Okay, if you divide this region, it is almost reaching the upper region of the pearlite. So this one is coarse pearlite. Coarse pearlite. Okay, so because of the marker structure different, so the properties is different. Martensite is hardest. Martensite plus a small amount of pearlite will be less hard. And then fine pearlite is more, fine pearlite, there's no martensite. Of course, it is very ductile. And most ductile is a pearlite or maybe coarse pearlite. CCC diagram simply give the various transformation product which will be obtained at different cooling rates. Okay, the end product are usually martensite or perlite, depending on the cooling media. It's not applicable for bainite. Okay, if you conduct normalizing or full annealing this process, you can use a CCT diagram. So normalizing, what's the difference? The difference is it cool slightly faster. Okay, and annealing the most slower cooling rate. So it's end here, which is fine perlite. What about full annealing? This is full annealing. Okay, the completion is fall at this region. What region is this? This is called perlite. Or sometimes it is you can obtain perlite, but not fine perlite. If you want to obtain fine perlite, you need to use normalizing process. The curve like this is a very short time. Transformation complete at the second about 10 until not 10, about 20 or 50 seconds. Okay, so look at the time. The time is very important. All right. I think it's 3:50. How many slides more we have? There are another 7 slides. I think we can stop now. We can continue next week on Sunday. Any question before I end the class? Because a learning element is it's quite long to explain this one. Any question?
No, Doktor.
Okay. If no question, I think I can stop here. Panjang juga nak cerita ni. Okay. I think that's all for today. See you again next week. And for those who